Welcome to a new video, and in today's video we are going to start this series of solving the questions of Erwin Kreyszig's Advanced Engineering Mathematics. And so in today's video we are going to solve the first 8 questions of the very first problem set, which is numbered as 1.1. So without any further ado, let's begin the video. The very first question is y prime plus 2 sine 2 pi x equals 0. Now, before discussing about how to solve this type of questions, let's first discuss the fact that whenever we're solving a differential equation, we most importantly need to convert this y prime as dy by dx. Because without that, we won't be able to, you know, take the dy by dx to the other side of the equation. Hence, the first step in solving any differential equation would be writing it as dy by dx. And in case you're wondering why we write dy by dx as y prime, well, that's because writing the original equation is much easier when we write it as y prime, or say when we have d square y by dx square, which is the double derivative, which is short form can be written as y double dash, and hence it's a much shorter way of stating our differentials when we are reading some text. But in case of solving the differential equation in general, we need to write it in this expanded form. All right, now talking about how we can solve this question, this type is the very most basic type. If you have studied it, we just need to take it to the other side, the function of x to the other side, and just integrate it. Now why is it so? Because this function is completely of x. In complex situations, the functions that we will encounter once uh, you know once we keep it aside of the dy by dx function, we see it's multivariable functions, mostly of x and y, and hence the thing is that there are certain complexities in solving those questions. We just can't take it to the other side and integrate it with its respective um, variable, right? Because then in those cases we will have a function with both x and y as variables, right? So we cannot directly integrate. And in this case, though, we just need to take it to the other side. Forgot to write the equal to 0 part, but you get it right. We can take it to the right side. We get a minus 2 sine 2 by x and a dy by dx in the left hand side. Hence, taking the dx element to the right hand side, we get dy equals this function into dx, and just integrating it, we get dy as just y, right? Now, how to solve this integral? First, we just need to say t equals 2 pi x, and hence if we differentiate dt with respect to x, we get 2 pi. Hence, we get dx is equal to dt by 2 pi. And hence, now that we have obtained the relationship between the differentials of x and t, we can simply substitute it into our original equation, and hence we get this particular integral, where we can clearly see we can cancel out the 2's and just take the minus 1 by pi outside, because these are the constants, and hence we get it outside, and integral sine t dt as our final integral. And we can clearly see that it's of the standard form of integral sine x dx equals minus cos x plus c, and hence we get that our differential equation is minus 1 by pi times minus cos of t plus c. This minus and minus gets cancelled out, so we get a positive cos t by pi, but t equals 2 pi x, right? So we get y equals cos 2 pi x by pi plus c. So that is pretty easy, I guess. Moving on to the second one, it's actually the very same kind, so I don't need to explain much about this one. Similarly, have a function of x that's uh, you know uh, separate from the dy by dx, right? And hence we can just take it to the other side, just like the previous question. Get minus x e to the power minus x squared by 2. We take the elemental parts to the respective sides, integrate it, and hence we get from dy we get y. And then how can we integrate it? Again, this very same kind. We just need to take t equals minus x squared by 2, since uh, upon doing that and upon differentiating it, we get this particular form, which is our standard form. As we know, e to the power x dx is equal to ex plus c, right? So just like that, you can solve this question as well. And just to show you, dt by dx comes out to a minus x, as you can clearly see, and hence dt equals minus x dx. We already had minus x dx, so it's more straightforward, in fact, as compared to the previous question. So we just get e to the power t dt, and hence since we know e to the power x dx integral is e to the power x plus c, hence our final differential equation is y equals e to the power t plus c. But we defined t as minus x squared by 2, right? Hence our final equation is actually y equals e to the power minus x squared by 2 plus c. Coming to the third question, which is y prime equals y. Again, converting it into dy by dx equal to y. We just need to take the dx to the right hand side and the y to the left hand side. But why is that? Because we always want to try to bring the differential or the elemental variable parts with the function of that variable to the same side, or else we cannot integrate the function directly, right? Hence, doing that, we just integrate it. We get dy by y and dx, but we know that dx by x is equal to ln x plus c, the integral of dx by x, and hence similarly we can say dy by y would give us ln y. Hence ln y equals x plus c, or y is equal to e to the power x plus c. Now we can simplify it in a quite beautiful way, which is like this. Now we know from the fact of exponential formulas that if we have, say, e to the power b plus c, we can write it as a to the power b, a to the power b times a to the power c, right? And similarly, we can write e to the power x plus c as e to the power c times e to the power x, right? And as you can clearly see, e to the power c is just another um, constant, right? Hence, we can just name it as lambda, and hence we can write the general equation in a much more beautiful form, which is y equals lambda times e to the power x, right? So that was our final answer for the question number 3. Let's go to the question number 4. It's just the same question, right? It's just the same question where we just have a different coefficient, right? Hence we just once again, interchange the sides of dx and the sides of y. We just solve this. We just got ln y, and simply integral of dx comes x. Hence, once again, y equals e to the power minus 1.5 x plus c. And similarly to the previous one, we can write it as y equals lambda e to the power minus 5, minus 1.5 x, right? The more beautiful form of writing the equation. Now, the question number 5 is a bit different. And in this type of question, we just need to solve it using integration by parts. And in case you've forgotten it or haven't even learned it, well, in integration by parts, we just consider two functions and we just decide which function to differentiate and which function to integrate. And since in this case, both the functions are equally easy to both differentiate and integrate. It doesn't really matter which function we consider as the first function or as the second function. So we just randomly choose e to the power minus x as the integrating function and sin x as the differentiating function, and hence just using the formula of the biparts integration technique, we can simply solve it like this. Now for solving this particular expression, we get this particular expression in the end, and as we can clearly see, there's another integral that we cannot solve directly, right? Like there isn't a proper um, form that's defined as this particular integral. So let's say it's capital I. Now, solving this capital I, just like the way we solve the y equals 4 e to the power minus x sin x dx, we get this particular equation, right? Now, if we see carefully, we get this particular expression, which is sin x e to the power minus x dx, right? But if you think carefully, 4 times this expression is just our y, right? And hence, we do not further try to solve this integral. We just put this capital I value back to our original, um, you know, equation. This capital I, after solving, we put it back to the equation, and we get this particular thing. And you know, uh, from taking the 4 inside, we get basically y, and taking this minus y to the other side, we see on the left hand side is 2y, right? And in the right hand side we get minus 4 to the minus 6 sin x, and just minus 4 to the minus 6 cos x plus c, and therefore dividing both sides by 2, I get this particular expression. So that's finally the solution for our question number 5. Now going further to the question number 6, we see y double prime is equal to minus y. Now in case you didn't know, y double prime basically means the double derivative of y, right? So writing it in this form, we get d square y by dx square plus y is equal to 0. Now there are certain other methods to solve these kinds of expressions, but I'm going to solve today with my favorite method, alright? And so in my favorite method, we basically multiply both sides with 2 dy by dx, alright? And just to let you know, I like this method a lot because I find it much more, beautiful in a way, and you will see why. Okay, now let's consider a variable t as a dy by dx whole square. Now, if we differentiate this variable t with respect to x, we get this particular expression, which is 2 dy by dx times d square y by dx square. And if you look closely, this particular expression is just right in our original expression, right? And once again, if we define a variable k equals y square, and if we differentiate it with respect to x, we get 2y dy by dx, right? And similarly, this particular expression is also in our original expression that we obtained from multiplying this with 2 dy by dx, right? Hence, we can simply convert it into this particular form, and we get this particular thing. And of course, multiplying both sides or just cancelling out dx from the left hand side, we get this particular expression, and just integrating both sides, we get dy by dx whole square plus y square equal to c, right? Now, taking y squared to the right hand side and square rooting it, we get two solutions, alright? The dy by dx equals root c minus y square, and dy by dx equals minus root c minus y square. But why is that true? Because if y square is equal to say x, um, then y is equal to mod x, right? And what is mod x? Mod x is basically plus or minus x, alright? Hence, similarly, we see there is a plus or a minus scenario, and we need to, of course, consider both the cases, alright? Now, let's first solve this particular case, and upon solving, we just need to take the y function. As you can see, this is a function on y. We take this y function to the left hand side since we have the dy element in the numerator in the left hand side. And similarly, we just need to take the dx small element to the right hand side, and then after this integration we get tan inverse of y by root c equals x. Similarly, if we solve it, we will get sin inverse of y by root c equals minus of x. Just taking uh, you know the sine inverse and converting into sine x, we get y equals lambda times sine x as the final solution. Now, if you're asking, well, why didn't you consider the plus or minus case? But if you look at it closely, in this case, we will get the constant as plus root c. And in this case, we will get the constant as minus root c. And we are taking both the cases as lambda, alright? Plus root c and minus root c. We're taking both the cases as lambda. So basically lambda can be both positive and negative, right? And hence we can just write this beautiful expression right here, right? Now, moving forward to the second last question, we have y prime is equal to the hyperbolic function cosine, uh, where we have 5.31x inside of it. Now, similarly to the original cosine x, we can just directly integrate it as sine of the hyperbolic of sine x, and hence we just solve it in the normal way. We take t equals 5.13x, differentiate it, get dx as a expression of dt, just put it, solve it using this just discussed formula, and hence we get this final expression, nothing too complicated. Now coming to the very last question, we get y triple prime equals to e to the power minus 0.2x. Now y triple prime is just equal to d cube y by dx cube, right? So you can write it as you all know, as d by dx of y double dash, right? Because just differentiating y double dash gives us this triple dash, right? Hence, writing as it, we just get, we just normally integrate it, and we get y double prime equals to e to the power minus 0.2x by minus 0.2 plus c1, just the normal methods that we just discussed in these questions. So I didn't really you know write t equals 0 minus 0.2x and all that. You get it right. I hope, hopefully you get it right now. And hence, looking at the next part, we see that we again write y double prime as d by dx of y prime, right? And similarly, we again integrate it, and be careful, we need to integrate this c1 so that we get c1x, and in the second last expression we get c2, and this constant becomes 0 plus 0.04, since minus 0.2 times minus 0.2 gives us plus 0.04. Alright, now again we lastly write y prime as dy by dx, and just take dx to the other side, and again considering c2 in our integral, we get this final monstrous solution of our differential equation, where three constants are present for our solution, right? So yeah, that was the very last question of this particular video. See you in the next video where we complete the first worksheet of this particular book. So See you in the next one. Bye bye.